Now we'd like to show that the function e to the x, the exponential function, is equal to its Maclaurin series, and here we mean for all x in R, and we need a lemma in this case. We won't show this, but you can show this though. There's different ways to do it. It's a good exercise, but the limit as k approaches infinity of x to the power of k over k factorial, or even k plus 1 factorial, this is equal to 0 for all real numbers x. Alright, so there's different ways to show this. You should do it. You should check it out. One way I would say is if you can show that the series converges for any value of x, then the limit must be 0, right? So that's a converse of the test for divergence. So definitely give that a shot. But what we'd like to do now is actually show that the Maclaurin series for e to the x equals e to the x for every value of x. So here's what we'll do. Let's suppose, I'll just write out some symbols here, f of x is equal to e to the x, and of course this means that the k plus first derivative of this function for any k, this is always just e to the x, right? Any derivative you take of e to the x is always e to the x. So this is true for all k. And let's assume then, we're going to take the Maclaurin series, right? So let's put our x naught equal to 0, and let's let delta be any positive number here. So in this case, you want to think of delta as being large. Sometimes when we use delta, we think of delta as being a very small number, but here we can think of it as being large. Then what we know is that for x less than or equal to delta, so for any x less than or equal to delta, then because e to the x is an increasing function, then the k plus first derivative of f at x is equal to, we already know it's equal to e to the delta, right? And this is always going to be, it's equal to e to the x. I'm sorry. The derivative is e to the x. I kind of jumped the gun there, because what we're going to say is that if x is less than or equal to delta, then e to the x is also less than or equal to delta. Okay, and this is because e to the x, right? So because f of x equals e to the x is increasing. All right, so there's a bound on our k plus first derivative. At this point, we can call in Taylor's remainder theorem. So let's remember, Taylor's remainder is the following. It says that the remainder, the kth remainder, r sub k, is bounded by the maximum of this derivative. So I'm going to write this as m over k plus 1 factorial x to the k, right? So this is true where the k plus first derivative of our function is less than or equal to this constant m. So if we can find a bound on our function, then the remainder is less than this bound, right, divided by k plus 1 factorial. So based on the work that we've done, what's our bound going to be? Well, our bound is just going to be this e to the delta, right? So since m is e to the delta, we obtain, right, the following formula, which is that our remainder, this remainder, rk of x, is less than or equal to e to the delta, which is a constant, by the way. We fixed our delta, over k plus 1 factorial x to the power k. And now we can take the limit, right? We want to show that the Maclaurin series equals e to the x. So what we have to do is show that the remainder, the limit of the remainder, is equal to 0. All right? And so this is what we get, right? The limit as k approaches infinity of rk of x is less than or equal to the limit as k approaches infinity of constant e to the delta over k plus 1 factorial times absolute value x to the k plus 1. So I've left the k plus 1 off of all these. That was a mistake. That's x to the k plus 1. And then, of course, e to the delta comes out. Again, constant, right? Limit as k approaches infinity of x to the k plus 1 over k plus 1 factorial. And at this point, we go back up and take a look at our lemma. And our lemma tells us just replace k by k plus 1. This limit must be 0, right? And so this limit is 0. All right, so on one hand, the limit of the remainder is, you can do absolute value here, is less than or equal to 0. On the other hand, it's because it should be absolute value, it's greater than or equal to 0, and so by the squeeze theorem, then the limit of the remainder, r sub k, as k approaches infinity, is equal to 0, and this means that e to the x equals its Maclaurin series. So e to the x is equal to the sum, and it goes from 0 to infinity, 1 over n factorial x to the n, right? And this is true for all x in R, all real numbers.